Today's lesson, I guess, is just about how to calculate mass defect and binding energy. So I'm going to show you this example. It's really, really easy. And because it's first period, I thought we would do something nice and easy. So they've given us the mass of a proton, the mass of a neutron, and then they've given us the conversion for 1 unit because they're giving us masses in units, and then MeV is electron volt. So that's what we're going to use to calculate the binding energy. So for the first one, it says tritium is an isotope of hydrogen. It is used in the watch industry as a radioluminescent material. It is laid on the dial and hands so that your watch can be read in the dark. The mass of the tritium isotope is, and then it gives you the units. So what I'm going to do is I'm now going to change to my iPad screen, and I'm going to transfer the data over there. So I'll show you how this works. It's really not complicated at all. So, all right, let me get back to this one. All right, so we've got mass of a proton, and that's 1.007825 units. And the mass of a neutron, 1.008665 units. And then we've got 1 unit is equal to, 1 unit is equal to 931 electron volts. So then they give us this isotope of tritium, and the mass is 3.01, 0.0160490 units. So first one, we have to calculate mass defect and then nuclear binding energy. So first, mass defect. Remembering from yesterday's lesson that mass defect is the mass of all of the components of a nuclide minus the atomic mass of the nuclide. So this is the atomic mass, and we're going to add up the mass based on the nuclear symbol here. So on the bottom, we have 1, which represents the number of protons. And this is atomic mass, which means there's 2 neutrons. So based on atomic mass and atomic number, we have 1 proton and 2 neutrons. So all we have to do is take the masses that they've given us here and add them up, and then subtract the atomic mass from that total. So if we take the mass of 1 proton is 1.007825, and then we're going to add that to 2 times the neutrons, 1.008665. And then let me get my calculator. Where is that? Yeah, up here. Okay, so go back here and then whoop, bring it over there. So we have, crap, now it's covered. We have 1.007825 plus 2 times 1.008665, and we get 3.025155. Okay, so that is the calculated mass of the tritium isotope of hydrogen. So now we have to subtract, where's my pencil? Now we subtract the atomic mass, which they've given us. So we minus 3.061, sorry, 60490, right? 3.0160490. Yep. And we'll bring back the calculator. Come on, calculator. Come on, calculator. There we go. So that's still up there. Minus 3.0160490. And we get the mass defect of 0.009106 units. Okay. So that answers the mass defect question, right? Because we talked about yesterday how when the nucleus is formed, energy is released. And so using Einstein's equation of E equals mc squared, we know that mass can be converted into energy. So the loss in mass of a nucleus is due to the loss in energy when the nucleus is formed. So when the tritium nucleus is formed, it loses this many units of mass. Now for the second question of nuclear binding energy, we're going to use this conversion that they've given us in the question, which is 1 unit is equal to 931 electron volts. So, excuse me, we're just going to take our mass. We're going to take our mass defect and we're going to multiply it times our conversion. I'm not going to actually do the actual conversion because you're in grade 12, so we've done that already. So it's multiplied times 931. So let's get the calculator out again. Hello, calculator. So that number is still up there. Now we multiply times 931 and we get 8.48. Get rid of that. 48 electron volts. And that's our nuclear binding energy.